All right, thank you, Xavier. That's a pleasure and an honor to be able to speak with you all. And if you have questions as we're going along, make sure to ask, and Carlotta will chime in and stop me and get to the questions. We're going to talk about water quality and turf grass management, and let me just get it. And the main things that we're going to cover are going to be the impacts of water quality on soil chemistry, and to do that we're going to use some examples. We're going to look at climate and rainfall patterns to see how those impact the use of irrigation water. If you have enough rainfall, then your water quality is not so critical. And actually it turns out, as we go through the presentation, you'll notice that it's really soil physical characteristics that are probably the major impact on how well your water works at your facility. We'll look at key water quality factors, and there's not as many as you'd think that you need to worry about as far as whether water is going to work on a particular location. Then big issues with irrigation distribution, hydraulic conductivity and drainage. Those things kind of work together. And then soil moisture issues, because they tie in. You can have a soil that drains really well but doesn't hold enough water to get you through a day. So this is an example of a site, and we're going to talk more about some of these locations, where you can see the irrigation head over in this. I get my pen here to help out. In this area is where the irrigation head's located, and that irrigation head has leaked a little bit, or it leaks quite a bit. Even though the soil is very heavy clay, the turf is doing well in that area, and the salts are down to 6 decisiemens per meter, which this is ryegrass overseeded Bermuda, and that works out pretty well. But just adjacent to the irrigation head, where it's 12 decisiemens per meter, the turf is failing. And that's just because there's not enough water moving through the soil to allow the turf to survive. There's too much salts accumulation in the soil. Maybe I won't use that pointer too much. Then if we look at another similar situation, and this is going to stress the relationship between salinity of the water and the soil type. This is a water that contains only 0.82 decisiemens per meter of total dissolved salts. So that's just not very salty water. It's a good quality water, but we're still seeing that the salt accumulation in the soil is up as high as 15 decisiemens per meter because the water just doesn't move through the soil. Where they've installed drainage systems, you can see that the decisiemens have dropped to 5.4 decisiemens per meter. And this is Bermuda grass. And it's only in this small area right over top of the drains. And the reason that the water cannot move into the drains from the sides laterally. So we'll talk about how we correct that type of a situation a little further in the presentation. And then this is not related directly to soil quality because there's plenty of good areas performing on this this golf course, but this is a low spot where all the water drains from the sides down to the center area that's too low, so that the fairway was not shaped properly to maintain a slope of at least 1% so that surface water can run off. So it just water puddles in this area and it doesn't work very well. So it's related to water quality and soil conditions and also the contours. So what we're going to talk about basically is water quality, quantity, and drainage. And it's those three things that tie together that will make for a successful interaction between those factors or not. This table gives a good look at the factors that will help determine whether a water is going to work at a particular location. And there's some conflicting data in this table that you'll notice. And we'll just take a pick from the top, and then we'll see how these things work a little bit later in the presentation also. But if you look at the salinity at the top, we say if you have less than 0.7 decisiemens per meter, there's a low likelihood that you'll have problems with the soil. From 0.7 to 3, the increase the likelihood of causing problems, and then above 3 decisiemens per meter electrical conductivity, you probably are going to have an issue. It's going to be difficult to manage. But then we look down here at the sodium absorption ratio, or SAR, and I'll show you how you calculate that a little bit later. And we see that if the SAR is between 0 and 3, which is very low, you would think that would be a great quality water. But you need to have electrical conductivity above 0.7 for that water to work. And if you increase the sodium absorption ratio to 3 to 6, the EC of the water has to be higher still for that water to be of use. And there's an interaction between the salinity and sodium content of the water that influences the water actually moving into the soil. If the water has a very low salt content, which is below 0.7, sometimes and frequently that water will not enter the soil very easily. So we end up having to amend soils with very low salt content with products like gypsum or calcium sulfate to allow that water to move into the soil. So you need to increase the salt in some waters to amend them to go into the soil. And I think we see almost equal number of problems with low salt water as we have with high salt water. Then the other factors we watch out for is the sodium content of the water and the residual sodium carbonate. This factor here is the one that will influence whether or not the water will take calcium off the exchange sites in the soil and slowly allow sodium to accumulate. But those are the ones that are most important: the residual sodium carbonate, the sodium absorption ratio, and the electrical conductivity. If we get a feel for those 3 numbers, we'll be in pretty good shape. And just as long as we're staying below 3 or 4 or 5 with SAR, you're not in bad shape. And if the salinity is below, really if you're below 2, it's usually manageable depending on the soil, because we saw that earlier, the 0.8 EC water having a problem with Bermuda grass. So it's a combination of the water and the soils that make it all work together. I just put this up as a reminder of the tolerance of turf grass varieties to soil salinity. POA is the most sensitive at 4 decisiemens per meter. Bent grass, ryegrass, kikuyu grass, which I don't think any of you have over there, around 6 decisiemens per meter. Bermuda around 8, and paspalum around 12 decisiemens per meter. And they'll perform fine at those levels. Now I want to use some examples to get some of these points across, and the one that I want to look at is from Colorado, and this is Colorado Country Club. It was built in 1908. It's been irrigated with this domestic water for more than 100 years. So this sort of gives you an idea of the quality of water that works pretty good. As you can see, the electrical conductivity is low, and we would normally call that possibly a problem water because the electrical conductivity is so low. The SAR is low also, and has very little sodium. About 10 years ago, they had to switch to recycled water. And so this is on the course. So we're going from this water, 100 years of this type of irrigation water, to now recycle water forever, just because of drought conditions, that they're trying to find alternative sources to domestic water. So the electrical conductivity went up 3-fold, but it's still in an all right area at 0.9 decisiemens per meter. So that's not too bad. The SAR went from 8 to 3.4. So we're talking about a large increase in SAR. Bicarbonate stayed about the same, and that will influence the residual sodium carbonate. But look at the bottom here, we don't have any residual sodium carbonate, and it'll see why that makes a difference in a few minutes. But sodium went from 20 to 103 parts per million. Now these guidelines on the right side give you an idea of what are good quality conditions for ryegrass. So it fits in pretty well with good quality water. Even the sodium levels are not that much higher than we would expect. Bicarbonates it's a topic that everybody seems to get concerned about, but typically bicarbonates are not a problem. The levels, the guideline levels, even this 50 parts per million, always seem to be too low. So the guidelines are probably off. Let's take a look at what happened in the course of the past in the course of about 6 years of irrigation. So these are the dates. This is 2002, when the water was changed from domestic water to recycled water. And this is the electrical conductivity of the soil. This is the average, and it shows you the variation. And they were able to manage the recycled water without any problem over that period of time. So that increase in salinity didn't seem to have an impact on the soil whatsoever. No problem at all. And the nitrogen levels, let me just go back up for a second. The nitrogen levels went from 0.2 parts per million to 16 parts per million. So really, that's a huge amount of nitrogen that's coming into the system from that recycled water. But still, they were able to manage it. And 20 parts per million in the water is, well, about 5 grams per meter squared in the top 6 inches. So it's a pretty heavy rate of nitrogen. But what really made a difference, and we saw the increase in the sodium, just the actual sodium in the water, is that we saw the water sodium level just increase like crazy. The difference between here and here is a rainfall, heavier rainfall year, and you can see rainfall does help move those levels down, but there's a steady increase in sodium that was a concern, and they haven't been able to manage that effectively so far. It would take a lot more gypsum, I think, to help displace that sodium. But above 110 parts per million sodium in the soil with the ryegrass or POA can increase susceptibility to rapid blight, which is running around Europe a little bit more. So this type of a trend is something that you need to watch out for. And I think one of the issues you want to monitor when you're looking at your irrigation water and use over time is these trends. I don't think you should take just one soil sample and assume that that's going to give you a representative of what's going on, because you don't know if the trend is going upward or downward unless you keep track of and keep records of your soil conditions. So at Denver Country Club, we saw those rainfall events. And there was one event where they had 64 millimeters of rain. And we monitored the soils just before the rainfall event and then just after the rainfall event. And we saw that there was a pretty significant reduction in sodium by 41%, sulfur by 67%. We went from chloride levels, 77% reduction, and then a 19% reduction in total salts. So just the 64 millimeters of rainfall, although this was in one event, so it was a pretty heavy rain, caused a very significant impact on soil conditions. So you can imagine that your soil salt levels are going to be increasing during the periods where you have to irrigate, but then when you have rainfall, and if you have rainfall frequently enough, you'll be in good shape. But I know in your southern environments are more like San Diego, we don't get much rainfall. I took an example from northeastern Spain in Girona as an example of rainfall conditions, and there's 737 millimeters for the year, and this is the distribution, and we'll talk a little bit more about that, but you can see there's going to be some months where it's going to be a problem because you have to depend on irrigation. And it's a balance between irrigation and rainfall that will determine how your soils respond to salts. In this case, this is a Los Angeles Country Club, and we ran a leaching study. We have to leach greens periodically in California to maintain salt levels below the tolerance of both bentgrass and POA. They had a moderate quality well water. We selected 2 greens to work with to pull samples before and after the leaching event. We were looking at different leaching methods on the golf course. And there were 3 locations in each green that we sampled before and after leaching to see how the salt management would work with this leaching practice. And the precipitation rates were evaluated in each of those locations to determine how much water really went on relative to the amount of water that we thought would go on. And the range of irrigation went from 20 to 69 millimeters per hour in precipitation rate. And this is common in a golf course green situation. Let me just show you why that happens. This is the outline of the golf course green. These blue dots represent the irrigation heads. The red circles represent the throw of the irrigation head based on the manufacturer's specifications. These are about 60-foot throws. And you know, ideally, you would have head-to-head irrigation. And this is pretty close. You can see the throw from this head reaches just about to the adjacent head. But the narrow component of the green here changes the distribution. I mean, the heads were placed near the green rather than possibly where they might be better located. These asterisks illustrate the locations of where the samples were pulled. It was a 1 cup cutter sample from each location, and they're pulled to a depth of 10 centimeters before they were leached, and then after they were leached. So we're going to take a look at how the soil responds to application of water. So this is a little different than rainfall because we're using just the same irrigation water, but we can see how the reduction in salts goes. This table illustrates how much precipitation was delivered in each of the 2 greens, green 5 and green 15. And this is site A, so this would be the front of the green that receives. Let me go back here for a second. If you notice here, only 2 irrigation heads impact this area of the green. And only 2 irrigation heads, these 2 irrigation heads, impact this area of the green. In the center of the green, all 4 heads deliver water to the center of the green. So that gives you an idea that the distribution is so bad, frequently bad, on golf course greens. And if we look in those areas that only received 2 heads of irrigation, they range between 20 millimeters per hour and 48 millimeters per hour precipitation. And they delivered a total of either 76 total millimeters of leaching irrigation for the duration of time that we ran the system, to 183 for the 2 heads. And where all 4 heads were hitting, it was 250 millimeters of precipitation fell during the leaching period in those cases. So you can see there's a dramatic difference in the amount of water that's delivered just due to the irrigation design of the system. So the reduction of those...
Larry.
Yes.
Sorry, just one question. There is a guy, Daniel Carretera from the Canarian Island. He's asking if this golf course, the Los Angeles Country Club, is the north course that you are talking about.
These were rebuilt, and I believe that is right. You're right. It's the north course.
Oh, okay. Just a curiosity. Thank you.
Okay, I'll try to speak a little slower too. Do I need to go back over anything so far?
No, I don't think so. But if you speak a little bit slower, the interpreter she's gonna be happy.
Yeah.
Okay. Thank you.
I'll try to do better. I was supposed to.
No, I know it's hard.
I'll go slower.
Okay. Bye.
Okay. So there was a reduction in salinity by 20% in salts, and there was no. This is using a 1-to-2 dilution that many laboratories use, as opposed to SPE, which is saturated paste extraction, which is a common technique for evaluating soil salt levels. So in this case, it turns out that the more standard laboratory practices using a 1-to-2 dilution seem to work well and better than the saturated paste extraction. When we look at sodium reduction, there is a 31% reduction on the average. So this is just all of those samples averaged together, and we're trying to keep the levels below 110 parts per million, and they dropped from 83 to 57. This is using MELIC 3 extraction. And again, we didn't see a change using saturated paste extraction. And I'm not sure why that happened, but it shows that MELIC 3 is still okay for this type of analysis. There was also a 45 part per million reduction, a 45% reduction in sulfur. And we didn't see the reduction in saturated paste extraction, and a 54% reduction in chloride. I think what it means to me is that in the cases of looking at salinity issues, when the salt levels are not high, or not that high, as in the case of Los Angeles Country Club, Melic 3 extraction is going to work well, and you don't need to use saturated paste extraction. That was just one test. We wanted to compare those two analytical practices because we use primarily Melic 3 extraction on soils, and it seems like it's okay, and that saturated paste did not provide additional information. Now when we look at, this is before the leaching irrigation, and we have precipitation rate at the bottom. So this would be 25, 50, and 75 millimeters per hour due to the locations of whether there's one or whether there's 2 or 4 irrigation heads impacting the area. You can see that over time, if you have low precipitation rates, sodium will accumulate more than when you have high precipitation rates. And this is just due to more water being delivered and salts just being pushed out during every irrigation event. When we look after the leaching practice, you would think that these would all drop down, and that's what actually happened. So now, after we put on that leaching irrigation, which the least water that went on was about 70 millimeters, you can see that all the salt levels, except for this one, all the sodium levels were reduced. So as long as you can put on enough water, you can manage the conditions in the soils. So the limiting factor that I mentioned earlier is really being able to move water through the soil is probably the most important factor, probably more important than the quality of your irrigation water. This was just taking a look at the locations of golf courses in Spain, and you have a wide range of environmental conditions. So I'm going to generalize a little bit, but I'm going to take data from the Girona area to work on that. For reference evapotranspiration, I used this publication that was looking at ETs, or evapotranspiration, from 1961 to 2001 at a variety of locations in Spain. And this will tie together with the rainfall. You've seen this graph already. So we're looking at annual rainfall, and you should have this roughly for your location because it will help determine how much water you're going to end up using for irrigation and how much leaching impact this rainfall will have. And earlier we're saying that if we get 60 millimeters, we have a pretty good impact on soil salt conditions. So areas where you're getting under 60 millimeters in a month, it's going to be a little bit more difficult to manage salts. You're going to have to manage the salts with the irrigation water only. The months that we anticipate there being a problem will be July and August up in this area of the country, because these are the two times when you're going to have very low rainfall. Now, if we compare that to evapotranspiration, and this is the data that was reported earlier, we can see that there's a nice trend over the course of the year, as you'd imagine, a pretty large range in July and August. In fact, June, July, and August are the months where you're really going to be dependent on irrigation, and hopefully, if you got some rainfall, it would be helpful. So if we look at the deficit, So if we take that average, so we're looking at averages. So this is just roughly in this location, roughly 500 millimeters or 5 meters per year, based on the ET and the rainfall. So we're looking at where the problems are going to occur, and it's going to occur in June, July, and August, where all of the water is going to be delivered from irrigation, a lot more water from irrigation. That just gives a rough idea of when we're going to see a problem and the amount of deficit. So let's take a look at how you would make the calculations on that amount of water that's delivered. If you have 1 millimeter, one part per million is equivalent to 1 milligram per kilogram. And what we're trying to do is figure out how much water will be deposited if all of the salts go into that top 10 centimeters of soil, with no leaching, no rainfall, no additional water to move those elements through the soil. The other factor that's nice is 1 liter of water weighs 1 kilogram. So you end up with a nice relationship between the amount of parts per million in the water and in liters. And also, if you apply 1 millimeter of water per meter, that will also equal a liter. So in that case, we have a nice equivalency. And if we use 1.5 grams per cubic centimeter per cubic centimeter of soil for the bulk density, 1 meter to a depth of 10 centimeters will be 150 kilograms, and a hectare of that soil will weigh 1.5 million kilograms. So if you applied, really, when you look at this, if you applied 1.5 kilograms per 1.5 million kilograms, that's 1 part per million in the top 10 centimeters. So if we come back and look at the water, parts per million of the water times the millimeters of water applied per year, that will give us the milligrams applied per meter squared. You're applying that over the entire surface. So if we take milligrams, that will be the total milligrams applied per meter squared, divided by 150 kilograms, that's the weight of the soil, per 10 centimeters squared, depth of 10 centimeters deep. You'll end up calculating the part per million increase in the soil. So you just divide by 150. So for an evaluation, if we have 13 parts per million nitrate nitrogen, and we're using 500 millimeters of water per year in the irrigation, that'll deliver 6,500 milligrams per meter squared. You simply divide by 150, and that will give you 43 parts per million increase in the top 10 centimeters of the soil. So it's very easy to calculate how much salt increase you would expect based on the parts per million in the water and the amount of irrigation you put on. The only factor that's not included in that is rainfall and leaching irrigation. So this, we're assuming that this is the worst case scenario in the top 10 centimeters. If we wanted to just look at part per million in the water, we just say 1 part for every part per million in the water. If you're putting on 500 millimeters per year, you'll get a 3.3 part per million increase in the top 10 centimeters of soil. So that gives you a rough idea, and that's equivalent to about 0.5 grams per meter square per year. Now, when we look back at this nitrogen example, putting on 6.5 grams of nitrogen per meter square per year, that will tie in a few minutes on how much nitrogen you might require over the course of the year. So all of these things will tie back into actual nutrients that are needed by the plant. Now, if we look at residual sodium carbonate, this RSC, you'll notice that even though we're talking about residual sodium carbonate, we're really not even evaluating sodium in the equation. The reason we aren't evaluating sodium is because calcium and magnesium are very tightly bound by calcium carbonate. So no matter how much calcium and magnesium are involved, all of this bicarbonate that's in the water will be tied up by calcium and magnesium that's in the water. So the leftover bicarbonate is the residual sodium carbonate, or residual. It's really just residual carbonate, but that residual carbonate will then interact with the soil particles and pull calcium and magnesium off the soil particles. And then the replacement is, of course, sodium. So this is the situation, is you want to make sure that your sodium residual sodium carbonate is less than 1.25, and to do that you can inject acid and actually remove the bicarbonate. This is one of the few molecules in irrigation water that you can actually remove. If you treat with acid, this will form this will form carbon dioxide and will just leave as a gas. So acid will remove the bicarbonate, and this equation will be more favorable, will reduce the residual sodium carbonate. The other method you can use is to increase calcium. And you can do this by injecting calcium sulfate into the irrigation water. And you would offset the residual, or the calcium carbonate. And we'll notice in the water examples that I'm going to show that there is zero residual sodium carbonate in most water samples at golf courses. But if you have a residual sodium carbonate problem, you have two methods that you can correct that problem. If your RSC, a residual sodium carbonate, is below 1.25, then you just need to monitor your soils and to be sure that sodium doesn't just continue to increase, as we saw in the example from Colorado, where the sodium just kept going up and up and up after years. Then you need to be more aggressive on displacing that sodium. The other water quality factor that we mentioned earlier was sodium absorption ratio, and this is the equation. It's just sodium milliequivalents per liter, and this will be on all of your water reports, so you can calculate this yourself pretty easily with just a hand calculator. And it's divided by the square root of basically the average of these two: calcium milliequivalents plus magnesium divided by 2. Pretty easy calculation. There's a more sophisticated way to look at sodium absorption ratio that takes into account bicarbonate in the system, and it's called adjusted sodium absorption ratio. And I didn't put it here because I haven't seen the application provide more effective interpretation methods than just the SAR. But if you're interested, let me know, and we'll send you the spreadsheet that you can calculate that also. Just a reminder again, because this is where it all comes together, is that you're really looking at soil salinity and trying to figure out how to keep it within the range of the turf tolerance. And these levels are, again, 4 for POA, 6 for bentgrass, 8 for Bermuda, 12 for Paspalum. One way to prevent salts from accumulating in the soil, and we saw there's 2 ways of dealing with salts once they're in the soil. You can leach, or rainfall are the 2 ways that salts will be reduced in the soil. The other way is to put on additional water during every irrigation. Now, we noticed in the Los Angeles example that the sodium levels in areas that received higher precipitation of 250 millimeters, or I can't remember now. Let me see. It was what the precip rate was. If they had a precip rate of 66 millimeters per hour, which is a pretty high precipitation rate, that was in the center of the green when there was 4 irrigation heads hitting the center of the green. With that high precipitation rate, the salts did not accumulate. So they're putting on more water than was needed to manage the salts. To get an idea or an estimate of your leaching requirement, which is the value that you need to put on above and beyond what the plant needs based on evapotranspiration, you would use this equation. It's the electrical conductivity, or EC, of the water divided by 5 times the tolerance of the turf, EC of the turf, minus the EC of the water. And for an example, we're going to use a water with an EC of 1.1 decisiemens per meter, and we know the EC of the grass tolerance is 4 decisiemens per meter for Poa annua. Then you would need to have a 6% increase in the amount of water every time you irrigate. If you needed to put down 0.2 or 5 millimeters of water, you would have to put down to meet the evapotranspirational needs. So the ET is 5 for the day. You would need to put on 5.3 millimeters of water to keep the water moving through the soil so it wouldn't dry out. So that's one way. If you had a 15, if your precip rate was 15 millimeters per hour on the system, you would divide by 0.25 to get millimeters per minute. You would need to run for 21.2 minutes. That gives you an idea on how you would calculate the leaching fraction that you would have to add in. So it's 6% more than you would otherwise. Now, when we look at growth, and we're looking at the Chirona of bentgrass, poa, and ryegrass growth potential. And if you're not familiar with that, you can let me know, and we'll figure out a way to get you some more information. But the weather conditions indicate that the growth will increase up through the months of May. It gets a little bit hot in June and July, and then it grows better again as it cools down. And if we estimate the amount of nutrients that are needed based on this monthly growth potential, we can come up with a table. And this is available, this spreadsheet is available for you also. But looking at the monthly average temperatures for the year, we can calculate the total grams of nitrogen per meter squared, potassium, phosphorus, calcium, magnesium, all of the nutrients that are required for the plant to grow. And if we look at how much that represents in the soil in parts per million, it will be pulling out with almost 22 grams per meter square of nitrogen. It'll pull out about 71 parts per million of potassium, 18 parts per million of phosphorus, 14 parts per million of calcium, 9 parts per million of magnesium. So that's what the plant is expected to pull out of the soil. If we look at the soil guidelines using this MLSN guideline system, we would want to see a soil test containing 39 parts per million, 108 parts per million potassium, 345 parts per million calcium, and 56 parts per million of the magnesium. So we can look at a water analysis and determine what contribution the water will have on the soil nutrient levels. So here's what we can do with a few soil tests that Xavier sent. This is the secondary water. This is with the water of an EC of 0.9 and an irrigation level of 500 millimeters. We would expect the EC, if all of the salts accumulated in the top 10 centimeters. So this is the worst case scenario, and it didn't move anywhere. There was no leaching, no rainfall. It all just stayed right at the top. We would see an increase of up to 3 decisiemens per meter. We'd also see calcium increase to 238 decisiemens parts per million compared to what the plant needs. Just to give you a rough idea, that you can get almost all of the calcium that the plant would require for growth from the irrigation water alone. We get more magnesium than we would expect to need, and we don't get much potassium. There's seldom a situation where potassium is delivered in the irrigation water that even comes close to what the plant requires. And you'll notice that sodium gets pretty high. Now, if we look at another water source, this one has 1.5 decisiemens per meter, and that's getting a little bit more challenging to work with. We see that we'll get increases up to 5.8 decisiemens per meter without any type of leaching, which you can imagine that there is no situation where it would get that high without some level of leaching. So that still would be, it'd be borderline for bent grass, but it would be okay. But look what happens to sodium. Sodium accumulates to 620 parts per million. So this is not really a viable situation. There would have to be some leaching irrigation or some rainfall to help manage the salts in this situation. But for sure, you're going to possibly provide all of the other nutrients that you're going to need, with the exception of potassium, at least calcium and magnesium. This is another example with 1.1. They're similar. You can see the trends. You just multiply by 3.3 basically to get an assessment of how much contribution the water will have to providing nutrients, and then what type of risk you'll have with sodium. All right, let's look at where are we at here? So this gets back to the original comment on soil conditions and the limitations that we have with the saturated hydraulic conductivity, and also with the issues of wilting point. And they sort of fight each other, because you want to be able to move water rapidly, but it's usually as the water moves more rapidly and the soils become sandier, you lose the ability to hold water. So there's a battle between being able to leach the water out with holding enough water for the system. The costs of cultivation are an issue, because we need to improve movement of water through the soil, and things like sand top dressing, with the target of trying to get the water conductivity to increase above 25 millimeters per hour. The leaching is difficult. It uses water to manage the salts, and it also causes problems with soil structure and wet spots, so leaching is difficult. And drainage, if you don't have drainage, I think just about any water quality is going to eventually fail. Even a very clean water will slowly accumulate salts over time. So let's take a look at irrigation distribution uniformity just for a minute. And none of the irrigation systems today apply water uniformly. And what you're seeing on the side of this fairway is an irrigation system that does not have any heads in the rough to throw back out onto the fairway. So these two heads provide water in a circle, but they miss the gap in between. So there's really, even the most state-of-the-art irrigation system is flawed. The best you can get is a 80% distribution uniformity, and it's more typical to have 60 to 70% distribution uniformity. And the only time you can even get close to 100% uniformity is rainfall. So it's a pretty tough situation. And here's what the problem is caused by. This is an example of how distribution is from the heads are displayed. Where the overlaps are located, you can see there's more water will be applied. Probably not exactly twice as much here as here, but a pretty large proportion more, as we saw in the Los Angeles Country Club example of the greens irrigation system. This is basically an area that only receives irrigation from one head, and this is the sort of illustrates the example we observed a couple of slides back, where there is no backup heads in the fairway. The best irrigation distribution occurs in this triangle that requires 1, 2, 3, 4, 5, 6 irrigation heads to impact this area. There's no way that you can get a very uniform irrigation distribution, even with the triangle head-to-head. This is the best case where there's 6 versus 5 irrigation heads in the center of the irrigation distribution. And I think many of you have observed this before. This just elaborates on that example a little bit, showing you that only 1 irrigation head impacts here, 2 irrigation heads impact this area, 3 impact this area, and 4 heads impact this area here. Yeah, so it's be 4 and 3, 4 and 3. So that is not bad. When there's 6 heads impacting an area, the distribution is okay, but it's still the difference between 4 impacting this area and 3 heads impacting this area. One way to try to understand the distribution of your irrigation system in areas that are good or poor performing is to use a 2-can test. And you put 1 catch can or 1 container, and it can be, those catch cans can be just about anything. There's specific irrigation catch cans that you can use, or you can get just a plastic shoebox to use to do the same thing. But you collect the number of milliliters after, say, a 10-minute run time or 25 milliliters of water. You collect the milliliters in the poor plus the milliliters in good performing area, and you divide by 2, and then you divide by the milliliters in the poor area, and that will give you what is called a scheduling coefficient, which that means if you collected 25 mils where the turf is not doing well, and you collected 35 mils where the turf is performing well, you would need to bring this low level up, you would need to increase your run time by 1.2. So if you're running for 10 minutes, you'd have to run for 12 minutes. That just gives you a simple way to calculate how you would improve the conditions in a bad area if it was due to deficit irrigation. So here's an example of what that would look like. This is the irrigation catch can in an area that's good performing, and then you put the same kind of a catch can where it's poor performing, and you can see in the same irrigation runtime, this container was filled up to this level, as opposed to just a little bit of water that was in the bottom. And you can calculate what's going on, or you can determine whether the problem that you're seeing with the graphs that you're looking at is due to irrigation distribution or some other factor. But probably the first thing you should do when you observe areas that are not performing well is to take a catch can test, just to find out if it's irrigation related. This is an example of where that was collected. We were looking at this poor performing turf all around this head, and we're trying to figure out what was going on, and we found out that the cause was distribution. And when we looked at the irrigation head, we noticed that the backup irrigation nozzle was broken. There were some of these nozzles that should have this flat dispersing portion on the nozzle. They had been knocked off, or they had been broken. And this type of thing resulted in the head throwing water over that donut sort of area near the green. And of course, we noticed what happens in these situations also is that because these areas are not receiving enough water, salt will also accumulate in those areas. So that it's not just drought, but salts will also accumulate. You can get some data on irrigation heads and how they distribute water from the Center for Irrigation Technology at California State, or you can test it yourself by just putting catch cans out from the irrigation head to determine how much precipitation you get per hour. And you can see there's a lot of differences in irrigation heads. Certainly you would want to use lower precipitation heads if you can in almost all situations, if you have the infrastructure to be able to keep the irrigation system charged with the right pressure. But this is definitely a better irrigation distribution than the 750s. The 830s are better for sure. There's also other issues. We saw a pattern going down the fairway previously that was due to just the way the heads were distributed, and that there were no backup heads in the rough. This situation is different. The irrigation heads are behind a tree. So this distribution problem is due to the location of the tree and the irrigation heads. And this is a really difficult issue to solve, short of getting rid of the tree or moving irrigation heads. This pattern will always be there. One other issue we have encountered in sort of checking these types of situations out, where we're looking at the precipitation rate, and this is these numbers are not in millimeters, but just to give you an idea, if you do a 2 catch can test example where the turf is performing well and the turf is performing poor, you can find out what might be happening if the precipitation rates are wrong. And this was due to a manual override at the irrigation station in the field. So the main office computer was telling the system to put out the same amount of irrigation in both levels, but it was cut back in the field. So there's many possible ways irrigation can be improved, and one of those is to make a check on a system to see if they're delivering what you were hoping to deliver, which the objective was 0.22. They got close to that, or what the computer was told was 0.22, and they got close to that when everything was working right, as long as there was not a station adjust in the field that cut back the amount of runtime. So some of the causes of, I guess I have to pick it up here a little bit. Soil type is going to be an issue. And you all are probably aware of those factors that will cause some problems in soils. The bottom line is that percolation rate needs to get as close to the irrigation distribution rate. So if you're going to deliver water at at 20 millimeters per hour, then you better have a soil that can handle 20 millimeters per hour. So you don't need a lot of cycle and soak irrigations to make things work. That's kind of hard to do on regular soils. That's the type of thing that happened in this photograph that I showed earlier. A similar situation here, but in this case, they were able to come in and sand top dress so that water would start to move on the surface of the soil beneath the sand. And let me just show you what that looks like. So this is one of the fairways that is not sand top dressed, and you can see a heavy clay soil underneath that doesn't allow water to move anywhere. So those French drains, or those drains, only work in a very limited area directly above the drain. When you come in and you heavily top dress, this is all sand top dressing that is accumulated. Water can now move vertically and then laterally sideways on the top of the clay over to the drain and to go to drain. So the turf works well. Is that a comment? No. Now if we look at the electrical conductivity in the sand, in no sand versus sand, well, this is, wait, excuse me. This is percent sand in the soil, the composition of the material on the top. Without sand top dressing, we can see it's down below 60% sand, and with sand top dressing, we got it up to around 89 to 90% sand. If we then look at the electrical conductivity, we can see that the ability to move water through the soil has allowed us to drop the conductivity at the surface from over 10 decisiemens to down well below the tolerance of Bermuda grass where the sand is located. So water is able to move through the sand and go laterally to drain so that you can maintain soil salinity and the tolerance level. Other problems include hydrophobic areas due to fungi and other problems which you will have to address using surfactants to correct. Systems like this, where there are just hydrophobic areas that are just the nature of the sand material or organic matter has made the area hydrophobic. And the yes, and this is just stressing the point that if your soils can't move the water, then it doesn't matter how good your irrigation system is, you're not going to be able to manage the salts. So the physical situation at the facility is critical, not just the soil types themselves, but also the contours. And wherever you have areas that don't have at least 1% slope, you're likely going to have a problem. So if we're talking about trying to solve these problems, the first thing you want to do is characterize the problem by monitoring soil moisture to make sure that it's a problem with irrigation or some other issue. Looking at infiltration tests to see if there is a problem with the way water moves through the soils. Irrigation audits to see if the problem is with distribution, not necessarily water chemistry. So I'm just encouraging you not to just jump on water chemistry right off the bat. Some physical analysis will help when you can compare. In all these situations, you can compare good performing areas versus poor performing areas that are nearby to help you decide if it's a soil physical problem or if it's some other issue that you're working with. Mapping the soils can be helpful, and then looking at characterizing the areas in those different locations. So the obvious solutions to some of these will be maintaining your irrigation system, like that broken backup nozzle, fixing those as soon as you can. Top dressing, if you have problem areas or problem fairways somewhere, you top dress so you can more easily move water through the system. You can aerate to improve the surface movement. It won't fix everything, but it will definitely help. And then improving drainage, if possible, will definitely make an improvement. So when you're looking at characterizing the soil, there's one website that this has been moved around a little bit, but it's a simple calculator that you type in percent sand. So you have an analysis for percent sand, silt, and clay. At the laboratories, they will usually use a hydrometer to make this measurement. You just need percent sand and percent clay, and the program will calculate the wilting point. That's the amount of water that's available to the plant. So if you have less than 11%, then the plants are going to wilt in this particular soil. And I'll show you what that looks like because we ran some tests on this particular soil. This is a soil moisture meter. It's a capacitance soil moisture meter, and there's lots of new ones out that you can use. And we measured soil moisture at the number 4, number 3, number 2, and you can see footprints where number 2 is located, and number 1, where you can see clearly there's drought or there's some kind of turf stress going on here. Well, what we observed is that at 4, this place where it looks like the turf is healthy, there's 26.9% soil moisture. And we know that at 11% is where permanent wilting point is going to be. At 3 is 28.9, so it's a little bit higher there than there, but they're still above the level that the turf would be stressed. We're starting to see some wilt at 14.3%. You can see some footprinting happening here. And then at below the permanent wilting point at 10.6%, you'll see that the turf is starting to succumb to low soil moisture. So these numbers all pretty well fit together, and you can start to get a confidence that you know why the turf is declining in an area when you start looking at some of these factors that are involved in turf quality. Of course, sand top dressing will help even on greens to move water through the system. And there's various recommendations on the level. It's either 100 grams per meter squared or more is fine. We have clients that like to use the Spiker Thunderbird top dresser. They have a little motor on the bottom to drive the system, so you get a little bit more uniform spread and you don't get so tired putting this material out. So that's a very nice top dressing tool. And to give you an idea what 100 grams, this is a number 30 sand, meets USGA specs, but it has fewer large particles like this one here. We don't want a lot of those in there. This is before a 10-minute irrigation, and this is after. So if you sand top dress with 100 grams per meter square and put down 10 minutes of irrigation, you pretty much can get rid of the material. This is an example of what it looks like. This is what we use for irrigation auditing catch can. It was located here, and the irrigation system was run for 10 minutes, and you can see that the bulk of the sand is into the system. So it doesn't interfere with golf play at all once you put a little irrigation on. Of course, any kind of aeration, solid tines, you don't necessarily need to use hollow cores all the time, but venting monthly will help keep the system aerified and water moving a little bit. We have practices out here where people will core air-fi fairways. Then they'll throw sand on top of the cores, and they'll vertical mow to break up the cores and incorporate the sand, and then drag to finish off the surface. It's a very nice process for fairways. And simple solid tine aeration, if you have fairways that don't move water well, periodic is aeration like this will really make things a little bit better. So in the end, what the most important thing you need to do is identify the best performing locations on the course. That's one thing that's really important, and you can audit the irrigation rates that are going on from the system, and then characterize the chemical and physical conditions using MELEC 3. That's a fine way to do it, and compare those to the poor performing areas, and help you identify what is going wrong is really the way to go. Okay, do we have any questions?
Hi, Larry. Thank you very much for your presentation. It has been really, really interesting. Yes, there are several questions. Let me read it for you. There is Michael Rogers. He was wondering on your slide about that you were calculating the amount of nitrogen applied to the soil by the irrigation water. If you are calculating with 4 inches or 6 inches or 6 inches of soil.
Everything was 4 inches.
4 inches. Okay, so he was doubting about it. Okay, there is another guy, Javier Gutierrez. He's asking if have you ever seen a problem due to high content of zinc? Is there any clear threshold about zinc? He says that he has 17.2 ppm of zinc. So,
you know, I haven't seen a problem with the zinc. I can do a little checking to find out if there is a problem, but at 17 parts per million zinc doesn't seem that high. But I can look. That's an uncommon one to be worried about. So I'll have to do a little bit of special looking. I'm not sure what that level would be.
Okay, if not, maybe he can mail you to solve the doubt. Yeah.
Absolutely.
Okay, great. Okay, Xavier Millet is a golf consultant. He is asking would be acceptable, which the distribution uniformity would be acceptable for you of sprinkles on a clay soil?
Oh, well, yeah, on a clay soil, I mean, the best that you can get is what you want, but I think probably precipitation rate is going to be the big issue. You want the distribution to be above 80, well, at around 80% if you can get it, but you definitely want to slow down precip, use low precip rotors rather than a standard sprinkler if you can, and then if possible, you would want to try to top dress to be able to apply more water. The other side effect of top dressing is that it provides a firm surface, and you don't have problems like this where you see rutting due to the soil collapsing when it's wet. If there's sand on top of that, it would not have that big of a problem. So I guess as high as you can get, but certainly at least 80% for distribution uniformity, and a precipitation rate just as low as you can possibly go.
Okay, great. Another question from Michael Rogers. He's wondering if the method MELEC 3 is the best method in arid zones?
Well, it's unless if you've got calcareous soils, then you probably would want to use, if you're looking at trying to get more accurate measurements on calcium and magnesium, you would want to use ammonium acetate extraction. But I've found that Melic 3 works fine on arid soils. Most of the soils I work with are in arid areas, and you pick up all of the you pick up more cations because the salt levels are some of the materials that you're picking up. But as long as you're running a salinity test, like that 1 to 2 dilution salinity test, you'll determine whether or not salts are high. And if salts are high, you need to address that before you worry too much about the composition. And usually when salts are high, you have plenty of nutrients, so it's never a nutrient deficiency situation in a high salt soil. It's always a problem with getting rid of the salts.
Okay, perfect. There are no more questions, so that's all. Thank you